how would you test the circuit board and how would you test the chip? Well, they have some road mapping exercises, and road mapping will say that the testing technology is always behind the technology available. So they make the chips and they make the circuit board, but we haven't got the tools, the microscopes or the testing machines to test them. So you've got to really keep up with that as well. So test and validation technique. Okay. Any questions? I'm going to do a quick exercise before lunch, the design exercise next. Unless you've got any questions. Yeah? Yeah? Photonic, yeah. Well, how is this? Light can blind you. That's the first time. Anything to do with lasers, health and safety. Don't point a laser at people of aeroplanes and field doing. But that's what, photonics, yeah. It's usually the interface. The photonic switches themselves have been working at the speed of light. So the problem as I see it is, how do you get the data into and out of? Because if you've got a photonic device, you may have to make light in the first place, process using light, and convert light back to electricity. Possibly, I think it's a bottleneck, yeah. But then you can go parallel. So if you can, I mean, it's possible you could have a system where you got an optical computer, call it, and some type of fiber optic into an alpha wave file and multiplex it, but then it's not parallel anymore. It's not been solved, I don't think. I was keen on this, but the device is a bottleneck, not the light. But I think it will come in for certain applications. So photonics is a big field. You could make a career in that field. Well done. Okay, so what I want to do next is just, I think I've put it on the next slide. For most people that know this, I'm sorry, but I'm just going to show people that don't know a standard state machine design process. A lot of you may know this already, but I'm just going to run through it so everyone knows when it gets to the laboratories a little bit more. So FSM means finite state machine. Okay, so just to put this in a nutshell, every digital circuit can only have a number of states. 10 states, 20 states, 1,000 states. So it's limited. And as a designer, you try and fix it. So what you do as a designer, you have to specify the states to start with. Or if you're in a company, your boss might come down and say, I want you to design something to do this. And you may have a logic diagram or a truth table, or you may have things. So then you design from scratch. So you design the states, and the design procedure, we give a state number. Each state should be unique when we start out. We draw this state transition diagram, STD. This shows how we move between the states, a bit like moving between the station with a train, A to B, then B to A to C, and whatever. It shows you what's required in terms of a ticket price. Another will move it to this state, and one will move it to this state. It's quite visual, so this state transition diagram used in other things like communication. We used to use it in the old days, using the telephone to pick up a handset when you had handsets, and what's the procedure to make the phone call. So it's used in other systems as well, but for electronic, it's to work out the sequencing. So when you apply the clock, if the inputs are in a certain way, it'll go from state A to state B. If they're in a different way, go from state A to state C, and so on. And if nothing happens, it should stay in the same state. It's got to be stable. Okay, so the key to this is, because it's a finite state, it's clocked. It only changes when you have a clock, which is an advantage and a disadvantage. So we draw the state table. Then the state table is in sort of English. It's showing you the state between them. You can't design in labels, so then you have to go to the assignment table. You convert and then we've got a final design. So I just want to run through them very quickly. And then after that, I'm going to show you the two basic block diagrams for state machine based on two different systems. So I'm going to write on this board. So we can leave that there. We're going to design an odd parity checker. Do you know what it is? Yes? Some people know, some people don't. Do you know what parity is? Some people do, so let me just, some people obviously probably know. Normal definition of parity is the number of logic ones in a sequence. Okay? So that is even, yeah? So you got 2, so you got 0, 0, 1, 0, so you got 1, 2. So you've got an even number of ones, that's even parity. Okay? If we do another sequence, 0, 0, 1, 1, 1, that's got an odd number of ones, so that's odd parity. So we used to use it a lot. Not probably still do, but you're too young. But in the old days, when we typed computers, we used to use teletypewriters, like a typewriter that communicated on a serial bus, and we had a parity check bit. Because the communication was quite noisy in those days. Now it's all digital, it's fine, you don't get any problems. So the parity checking are not to be added in. So you've got 7 or 8-bit data, it just adds up the number of ones in it, and it says an odd or an even parity, so it checks it. So it's really used for transmission of data, but it can be used for anything, in arithmetic or whatever you want really. So I'm just going to show you how you can design a simple circuit to check. And the stream coming is a continuous stream, not just a fixed stream. So it's fairly simple. So design. Okay, so what we get when we're designers is you look at the question. Okay, we've got an input stream. So how many inputs have we got? 1. Okay, input stream is serial input, so only 1 input. That immediately simplifies the circuit. So we've got a circuit, so we've got an output, and the stream. So the stream is like a drum, it's just going to come in, 0, 1, 0, 1, 1, 0, and so on. So if we're thinking about a number of states, because we could only have even number or odd number of bits, we can only have 2 states. So we keep it simple. So we do the state transition diagram first. So start off, normally we'll draw the state. So got an even state inside this bubble, and we put the output down. We'll say the output's 0 for even parity and 1 for odd parity. Okay, so then how do you move between the states? So these are bubbles, so you draw like the state arcs. So if you're in the even state, you move to the odd state, you're looking for a 1, logic 1 to come in. So that's taking it from an even number to an odd number. If you're in the odd state, you're looking for a 1 to come in from that state to go back to there. So if the input was 1, 1, 1, 1, 1, you just cycle around, then when you get to the north, yeah, well, say you've got two, say you're up to there, and this one even, then another one comes in, go back to there, the next one comes in, go back to there, so cycling around, so, yeah. This is the state, so normally people don't show it, but on this I'm going to show what happens if we stay at north, stay at that state, and this one, stay at north, stay at that state. So just to describe that circuit, it can only be in two states, so just one more line to squeeze in. So circuit can be one of two states, even or odd. When inputs to one, we switch between the states. As I said earlier, even add another one, we go into an odd parity, add another one, go back to even parity. So if input is a north, we stay in the current state, but we've still got the same number of logic ones. And then the output associated with odd and even, I'm showing them a state bubble in here. And again, this is the first thing, as well as doing the bubbles, we decide as designers what the output should be. We could have chosen one or no the other way. As long as you've got your own specification and you understand it, that's fine. But once you've done it, you don't want to change it. Okay, so that's the specification. So input values that cause a transition are represented by the outputs that I've shown on the diagram with their associated inputs. So one thing is missing from that design now. Anybody any idea what's missing? Start. Well done. Most people, and a company called, oh, I can't say the name because it's an unknown semiconductor company once made a big chip, very big chip, and forgot to put a reset signal on it, reset input. You can't reset to a known condition. You don't know where you're starting from. So, if you look at this, again, we're not looking at textbook engineering, which is a bit more like a textbook type design. What's the real design practice for? You have to reset a circuit to a known condition. So you may see that design or similar designs in a textbook, but we never put reset on. So you put a reset, and I'll decide to reset to north. So when we do the final circuit, we're not just going to do the sequence. We're going to have a pulse. Start it at 0. Okay, and that's the same for simple circuit like this or the latest CPU. When you boot up your computer, you want to reset it so it hopefully starts from the same point. Well, things can go wrong. Never mind. So we'll just continue on with this. It won't take too long and should take us up to the lunch. Okay, so I know you all, did you enjoy the high tea? So you're probably not so ready for lunch, but I'm sure we can enjoy it in 10 minutes or so. So I'll just rub out the top and we'll do the design. So we'll do the state table. So again, the first time we do it, it's not so easy. We've only got a present state and a next state. We've got one input, which is on there, and one output. So let's look at the states. So we have even states. If we've got even states, the input coming in is only a 0 or a 1. Okay, so we know we need two even states. So even state with a 0 and even state with a 1. Okay, then the odd state, again we've only got two inputs, a 0 or a 1. So we've got odd state, a 0 or a 1. Now you're going to help me fill the table in, just so you don't go asleep before lunch. So if we're in even state, the input's 0, what's the next state? Yeah, very hungry. And what's the output? Output is changed. Okay? So now you're in even, you've got a 1, so this time going down. So that's odd. And the output this time will change. So the beauty about clock design is the output won't change until we have this clock in this type of design. So the next one, odd, and a note comes in. So we're going to stay in odd, yeah. And so the output stays node. and odd, and the 1 comes in. We're going for lunch, so we're going for even. I made a mistake. You see, I'm just testing. Okay, so present state odd, input is north, we're in north. I'm getting confused because we're already in north. Anyway, so we stay there. This guy's good. You can do the last one there. So odd with a 1. This time we're going back up to even. And this should be a north. Okay, so that's, oh sorry, that should be a 1. Yeah. So 2 things, I made a mistake there myself. 2 things we need to think about. This is the output, so the mistake I made is here. Okay. So it just shows you simple design can make simple mistakes. So what we're doing, present state, this is the present state output. Okay. So if we're in even state, the output is always north. If we're in the odd state, the output is always 1. So we do the clock. When we do the clock, instead of the next state, with a north we're still in even. If we're in even, the next state we're changing, going to odd. But we don't change the output till the next state. That's the beauty of the clock. It's clocked through. The feedback comes through the clock. So now we've got that, we can't design, we need to decide what values do we put in here, binary values for even and odd. So we've only got 2, so we only need 1 bit, and also 1 will cover it. If you add 4, you're going to need 2 bits, and so on. So I made the decision, whether it's right or wrong, it doesn't matter, it gets the engineer's decision, even as an output of north, so I'm going to make even north. Odd as an output of 1, I'm going to make odd 1 in my design. You could have chosen the other way. The difference will probably be you might need 1 extra inverter in the design. So you could try both ways if you've got time. You know, if you're working on the design industry, try both ways, it won't take long. just so you know where that comes from, we've assigned even on the present state to a north and not in the present state to a 1. So now There's one thing missing. Can you spot it? Reset. That's right. I left it off deliberately just to see how desperate you are to get your lunch. And I hope you enjoyed it. And I hope you enjoy your lunch.